So I welcome you for the DC motor control for EV application session. So in this session we are going to discuss in detail about basics of the DC motor and working principle of the DC motor and what all the types are available and how we can understand the speed control, and finally we can see the Matlab demonstrations. Are you ready to learn this concept? Please comment in the comment box. Ready? Yes. Thank you. Thank you, participants. Thanks for your reply. Yes. So now let us discuss about the DC motor. So the DC motor generally it's available in various formats, like from the basic small size to bigger size. See here in this motors. See here there are lot of types of motors are available actually in the DC motor alone, and for small toys car applications as well as that bigger size I mean EV traction motors also, EV traction applications. So based on the application the motor size has been varied, but still like vibration motors or small toy car motors, the DC motor is perfect choice for those applications. So here you should know what is the type of applications actually in this as per the type of applications. So like you can identify whether constant speed applications or variable speed applications. Can you tell me EV comes under which type of applications? EV comes under the various speed applications, whereas for the constant speed applications, can you tell me any one example for constant speed applications? So for the constant speed applications is like a lift and then a hoist motors and any other like lathe machines. So these are all the constant speed applications, right? So now let us take the working principle. So in this in the DC motor, so there will be a two major part. One is called stator and another one is called rotor. So the stator will be a permanent magnet and then rotor will have a coil. So whenever you are applying voltage to the coil, see whenever you are applying voltage, whenever you are applying voltage to the coil, that is a plus and minus. So via this brush and then slip ring, via this brush and slip ring, this voltage will be applied to the coil, right? Suppose if you are applying voltage to the coil, suppose if you take this is the plus terminal and then this is the minus terminal. See here the north and south will get reflect each other. So in that case that this coil plane will get moved to the other side. So like that when the coil plane moves other side, then automatically the brush will connect to the negative side, negative voltage. So in that time so this will be the negative and then this will be the positive. So in that case again the north pole will reflect and the coil will get reflected from this towards this direction. So like that the entire rotation is comes. And see here, this is the basic formula to understand the magnetic force as well as the torque. Right, see here the magnetic force is equal to BIL. So here the magnetic B is nothing but the magnetic flux density, current is I nothing but the current, and L nothing but the length of the conductor. So if you want to vary the magnetic force, then you have to vary whether you have to increase the length of the conductor or else you have to vary the current. So this is the basic principle of speed control mechanisms. So now let us check how to control the how the motor is working. See here, if you apply voltage here, so like a positive and the negative. So due to the reflection principle, the rotor will get reflected each with respect to the stator coils. That is called stator magnets. Right. So this is a stator magnet. So based on this principle, the DC motor is going to run. And types of the motor. So this is the type of the motors: DC separately excited, series motor, shunt motor, compound motor, and then permanent magnet DC motor. So these motors will have a high power motors, and then PMDC motor will be a low power motor. And how we can implement the speed control mechanism. So there are three different type of speed control mechanism. One is called flux control. So in the flux control, so you have to keep a voltage for the constant in the armature side. The field in the field winding, you are going to vary the voltage by implementing the variable rheostat. So this is the variable rheostat, and whenever you are changing the field current, then the speed of the motor is going to vary, right? Similarly for the armature rheostat, so the same instead of field, if you keep the rheostat in the armature side, then you can get the armature rheostat method. And similarly for the both the method are needs a variable rheostat. But here if you vary the voltage, if you are if you are changing the applied voltage from 0 to maximum, then we can get the variable output voltage. At the same time, if you vary the current, then you can vary the speed current, DC motor torque also. Yes. Dear participants, my humble request, don't spam the chat. So others are peacefully attending the class. So if don't spam the chat. So if you are keep on spamming the chat, then we will put your timeout share mode. So please follow the community rules. And see here, others are waiting. Others are listening the class. So don't spam the chat. Thanks for understanding. Yes. So now let us understand the speed control, how we can implement the speed control. See here, if you take any DC motor, so we need 4 MOSFETs, right? So if you again you can keep a single device to vary the speed from 0 to maximum speed or rated speed, but it's a single quadrant. So whereas for the DC motor in our EV applications, we need a 4 quadrant operations. So in that case, we need 4 MOSFETs. As per the SCR or triac, similar switches we are going to use it here, either IGBT or MOSFET. So based on the power level, you can use the devices. You can choose the device. So in this applications, we are going to choose 4 MOSFETs, switch 1, switch 2, switch 3, switch 4. So these are all the 4 MOSFETs which are going to use for these applications. So now the motor is in standstill position. Suppose if you apply a PWM for the switch 1 and 2, 4, so in that case the motor will rotate in this direction, or else let us take anti-clockwise directions. So direction is if you want if you want to run the motor at this direction, you have to enable the motor. You have to enable the switches S1 and then SW4. Similarly, if you want to change the direction, then you have to enable SW2 and then SW3. So how you can control the speed? See here, the pulse width is going to adjust. So the on time, if you vary the on time of the pulse, then we can get a variable output voltage at the motor terminal side. So if you vary this, if you are applying this kind of voltage to the motor, then we can vary the motor speed. So how you can generate this kind of pulses? By using the pulse generator in the Matlab, you can vary the you can generate the pulse width modulation. Similarly, in the real-time applications, you have to use any one microcontroller to generate a variable pulse width modulations. And this is the reverse direction. So for the clockwise direction, you have to enable switch 2 and then switch 3. So like that, if you generate a PWM, then we can vary the motor direction, as well as that we can vary the speed also. So this is as per the theoretical concept. And if you take a real-time motor control, so there are generalized block diagram for any motor control. See here, let us take this one. This is the motor, like a DC motor or induction motor or BLDC motor. First you should develop a microcontroller. So here you have to choose any one microcontroller. If you want to run a motor in the open loop applications, you can use any basic microcontrollers like Arduino or 8051 or anything. If you want to run the motor in the closed loop application, then you have to choose higher order high power microcontrollers like a 32-bit or 16-bit microcontroller. And in that one, like microchip based DSPs or ARM processors or DSP, I mean Texas Instruments based DSPs or FPGA processors. So these processors only going to give you closed loop control mechanisms. So first you have to identify the microcontroller, and after that power devices. So once if you connected the power devices, then you have to sense the parameters. So what are all the parameters needs to sense? One is the current of the motor. Similarly, motor speed and then positions. Suppose majority parameter of major parameter of this for the DC motor is armature current as well as that motor speed. So these two parameters enough to regulate to implement a closed loop application. And for the measuring the speed sensors, there are a few methods are there, like a tacho generator, magnetic pickup, optical disc, rotary encoders, and then Hall effect sensors. So these sensors are going to use in the real-time applications. Similarly, for the current measurement purpose, shunt resistance method, Hall effect method, and then current that is CT, current transformer method. So these three out of three one you can use it any one of this method. And for the power devices, drive nothing but it's a combination of circuit with the help of MOSFETs or IGBTs. Right? For the inverter applications, generally we will choose either two of these devices, any one of these two devices. And similarly, for the in the microcontroller section, you can use microprocessor or microcontroller or ARM processor or DSP processor as well as that FPGA processor also. FPGA processor also. Yeah. So FPGA. Right, similar kind of processor you have to choose. So you have to develop application code from the computer via the USB or Ethernet. You can download the application code to the microcontroller. So this microcontroller will sense the application code, and based on the application code it will generate a pulse width modulation. So this is the generalized block diagram for the motor control applications. So instead of DC motor, if you keep three-phase, I mean induction motor, so in that case you are going to keep a three-phase inverter with three outputs. So for the BLDC and PMSM and SRM, so like that. So this is generalized speed control mechanism for any motors. So just to keep in your mind, based on the motor type, you have to choose the PWM generation logic. So now. So let us move to the Matlab demonstration. So here first let us develop the motor and motor starting method, and then we can implement the motor control methods. Yeah. So now I'm going to open the Matlab. So just open the Simulink, create a new block. Just to save the simulation first. So day 10, experiment 1. So now open the library browser. So go to Simscape and electrical and specialized power systems. See here found fundamental blocks. See here the machines block will be here. So just to take a DC machine. First to take a DC machine. So just to take a DC machine, see here in this DC machine, there are few terminals are available. One is called A plus, A minus, nothing but armature plus and minus. Similarly, field plus and minus, and then TL nothing but you can apply a load to the motor. Right. Similarly, the M nothing but the measurement port. So to measure the motor parameter, then you have to take a bus selector component. Yeah, bus selector component, just to connect to the M terminal, then you can get a block. So just to open the bus selector and then remove by default signals and select whatever you want signals. So just to take speed. So this three signals is enough to generate to measure the motor parameters. And now we have to choose the type of the motor, like a rating of the motor. See here, so just to open the preset model, see here 5 HP 240 voltage 1750 RPM and then field voltage. So like that you have to choose one. So whatever you have, you can use this one. and then the mechanical input for the motor is, that is nothing, it's nothing but you are going to drive a you are going to apply a load to this motor. So that's it. And take a DC voltage source. To take a DC voltage source. So DC VDC for armature. And similarly for the field. So this is for field. VDC for the field. See here, the armature is 240 voltage, just apply 240 voltage, and then for the field you have to apply 300 voltage because its nameplate details is 300 voltage. So now you have to connect. Yeah. So now we have connected, and take a scope block. Take a scope block and apply here. So the three waveform we are going to analyze it. So to run the motor in the RPM, so you have to add gain block. See, by default the speed will be radian per second. If you want to convert to the RPM, so 30 by pi. So this is the radian per second to RPM conversion. And now we have to include the power guide block. See here, power guide block, so it's a three different simulation type. One is a continuous and then discrete. So let us take a discrete to get a fixed fixed sample time. And TL nothing but the load input for the motor. So just to take a constant block to apply a Newton meter. So how much torque you need, you can apply as a load to the motor. So just to take a constant block, and here you can vary the value from 0 to maximum full load torque. Just remove it, constant. Yes. So now I am going to apply 1 Newton meter. So let us observe what is the speed responses of the DC motor. Now let us wait for the simulation running. Yeah, so the simulation is closed. See here, the load is very limited. So by default, you have to change the scope settings. Yeah, so now we can see three different graph. So this is the first one is the radian, motor speed in RPM, and second one is that armature current, and third one is the electrical torque, electromagnetic torque. So now see here now, which means that the motor is not loaded, right? So that's why the motor speed is shows that 2000 above 2000 RPM. See here, by default the full load speed is 1750 RPM. So now we have to calculate the full load torque. So what is the full load torque? So what is the full load torque? See here, P is equal to T into omega, right? So now the P nothing but our motor power rating is P is equal to 5 HP into 746. So this is the P value, and T is nothing but the full load torque. So now we have to verify the omega. So omega is equal to 2 star pi star n, that is 1750 divided by 60. So this is the omega value, right? So now the T is equal to P by omega. So this is the full load torque. So like this you have to calculate the full load torque. So now you can apply a 20.35 value. So just take it 20, you can apply 20 Newton meter. So like that it will give you the output. So 20 Newton meter. Yeah. See here, electrical torque is generated to 20 Newton meter, and then speed is reached to the full load speed 1750 RPM. So this is the method to start the DC motor. So now we have to implement the DC motor speed control mechanisms. So to implement the speed control mechanism, so what we have to do? So we have to implement a speed control mechanism. So for that one, you can have a single single quadrant chopper and then 4 quadrant chopper. So to how you can vary the single quadrant? So just take a MOSFET. So just to take a MOSFET and disable this show measurement port, and take a armature volt supply terminal, and connect in between the MOSFET, between the source and then load. You just connect the MOSFET. Now we can control this switch via the pulse generator. So take a pulse generator block. So just take pulse generator block and then get the period. So it should be less than that value. So generally it will be a kilohertz range, like 1 kilohertz or 2 kilohertz or 5 kilohertz. So let us take 1 kilohertz. So the period is 1000 hertz or 1 kilohertz, and pulse width is now it is in the 5 percentage. So let us take a 99 percentage. So in that case, the entire voltage is applied to the maximum. So in that case, yeah. See here. So this is very simplest logic to implement the speed control mechanisms. So now let us try to run the simulation. See here, if you take a single quadrant chopper, you have to add additional circuits also. But for concept understanding purpose, I kept a single switch only. But here by default, we have to connect a inductor and then filter capacitor, and as well as the diode block also. So now we have applied 90%. See here, the same voltage has been applied. So now if you change the pulse width from 99% to, let us take 20%. See here, the graph is like 1750 RPM. So full load, fully rated speed we have achieved. Whereas if you change the voltage here, by reducing the duty cycle. So earlier it was a 99. So now I have applied 20%. So let us check what happening. See here, the speed approached to the 0 because the fully loaded conditions. So now see here, so just increase up to minimum worst case. In the worst case, like just to keep it 70%. So by changing the pulse width modulation, then we can vary the voltage. Yeah, see actually for low motor is fully loaded, so that's why it shows that. So let us reduce the load. Yeah. See here, as per the speed, as per the pulse width, it shows some value. Similarly, if you change the duty cycle, then we can vary the output DC motor control. Right. So this is the basic mechanism to control the speed of the DC motor. Okay, right. So now let us move to the next example. See here, we have so this is a single quadrant chopper. Similarly, we can go up for the 4 quadrant chopper also. So in that case, just change this one. So just to change this one, just to remove the terminal connections. Just remove the connections and rotate the devices. See, instead of single MOSFET, we have to keep a 4 MOSFET. So this is M1. So let us take SW1. and SW2, and similarly take SW3 and 4. So now just to connect MOSFET here. Just to connect MOSFET here. Yeah. See here, we are going to connect the armature plus terminal and then armature minus terminal. Yeah. So now we have to apply a pulse width modulations for these 4 MOSFETs. So just to take a pulse generator block. See here, this is the basic pulse generator block, 1 divided by 1000. So this is the period, and then pulse width we can keep it, and so just to connect the S1 and just to take a go-to function. So this is the common pulse for the SW1 and 2. Alright, so take a from block SW, same block SW1 and 2. So just to rotate the block. So this is the same pulses. Now we have to apply for SW1 and 4. Right, so just to take another model and then connect here. And similarly, now we are going to take a NOT gate. See here, just to take a NOT gate. Yeah, and this is the pulse for 3 and 4. 3 and 4. So just to take a scope block, from block 3 and 4. See here, if in this portion, if pulse width is more than 50%, more than 75%, the motor will be in the forward directions. If it is less than 25%, then the motor will be in the reverse direction. So let us check, let us keep it 75% and let us analyze the graph. Let us analyze the graph. So just to run the simulation. Yeah, see here we have applied 75%. So due to that one, the motor speed is in the forward direction. Similarly, if you change the pulse width from 75 to 25%, so the same parameter, then we can get a motor in the reverse directions. Yes. So similarly, we can vary the reverse direction. So this is the very simplest method to achieve a I mean 4-quadrant operations, right? See, if this is very generalized method, but in the real-time applications, so we have to take a 2 block. One is called a triangular waveform. See here, the triangular waveform, just to take a repeating sequence. And let us take the sine triangular waveform from 0 to 1, right? 0, 0.5 and then 1. And then frequency divided by 1000, 1 kilohertz. And then value 0, 1, 0. So now we can get a triangular waveform. And if you compare this triangular waveform with a constant value or DC voltage, then we can get a same kind of PWM in the real time, because actually by default pulse generator model will not be available in the real time. So for that one, we have to take a triangular. We have to generate a triangular functions as well as the control waveform. So by changing the control waveform, then we can get a controlled output voltage. So take a for controlled output voltage, take a constant block. Constant block. So now let us take a relational operator. So now we are going to compare this one. So whenever the triangular waveform is higher than this one, then the output will be high. So in that case, this is the switch 1. So this is the switch 1, and so the inverted voltage is the switch 2. Alright, so just inverted voltage is the switch 2. So just to take a NOT gate, connect here. So this is switch 2. This is switch 2, and this is switch 1. Yes. Similarly, again you can take the same graph. So let us change the logic. Same one. And this is the PWM for the next phase. That is at SW3 as well as the SW4. Inverted one. SW3 and SW4. So like that, this is another logic. Actually, I have developed this. I am using this logic. So if you are whichever your logic is comfortable for you, you can develop your own logic. So there is no any condition to follow the same logic and all. So only thing we have to apply a alternative power pulse width modulation for the same limb switches. And now we have generated this one. So now if you change this value instead of 0.9, then it will give you the motor will rotate in the one direction. Similarly, and the other direction also. So this is S3 and this is S4. Yes. So this is again real-time equivalent logic which is developed. So from this we have to generate a forward motoring, reverse motoring, and then braking mechanism also. So do you have any idea about the braking mechanisms? How we can implement the braking mechanisms? See here the reverse direction speed is applied. So now if you change to the 0.02, so in that case the motor will be rotated on the forward directions. Alright. So like this, once if the speed is settled, then after that there is no any deviations. So now we have to apply a braking mechanism. So how we can generate a braking mechanism? See in this circuit, whatever either directions like forward directions or reverse directions, we have to remove the top switch pulse, and then we have to enable the bottom switch pulse. So in that case, we can generate a braking mechanisms. So for that one, I am going to use another logic. So anyhow, this is the pulse width modulations. This is the controlled pulse width modulation. So I am going to use a switch case for braking mechanisms. So let us take this one. So let us take this one, and see here we have used 4 MOSFETs. Okay, so this is 4 MOSFETs we have used. And now if you change the pulse width modulation for this two MOSFETs, so see here PWM and then PWM, same PWM. If you apply, then the motor will be in the forward direction. Similarly for this one, so this is the pulse and then this is the pulse, then the motor will be in the reverse direction. So by changing the duty cycle, then we can get a variable voltages. Similarly, how we can implement the braking mechanism. So if you take this forward direction, in this one you have to remove the PWM, then at the same time you have to enable this one. So the same PWM may apply here, but here you have to enable the pulses. So either you can apply a constant pulse at the same time for the bottom switches, then we can apply a brake. So this braking mechanism is common for both the forward direction as well as the reverse directions. In the regenerative braking, the similar kind of logic we have to use. So we have to we need an additional circuit. So this from the motor terminal, like armature terminal A plus and then A minus. So the additional circuit needs to be connected. So this circuit will generate a will capture the voltage and then will store in the super capacitor or ultra capacitor. So and after that again we have to put on the circuit and then stored in the battery. Right. So this circuit will be like this one. This is one MOSFET and another MOSFET, inductor and then filter component and additional circuit. So this is called regenerative braking circuit. So this circuit needs to be applied. See here, this is also regenerative braking, but we are dissipating the generated voltage within the loop itself. So in that case, the speed will be straight away it's reached. If for example, if it is a forward direction, if you are enabling these two two switches, so in that case, the speed drastically will reach. The speed will reach to the 0 position. So let us check this logic how we can implement in this one in the Matlab Simulink. So just to take the same one. Now I am going to use the switch case. So take switch SWTCH switch case. See, actually the switch case nothing but whenever the logic meets. See here. So this is the logic input. So the threshold value, if there is a greater than 0, there is a greater than 0. So which means that okay, if you apply threshold value 0 here, see if the value is above 0, in that case this our input will be connected to the output port. Suppose if the input the control signal is less than 0, in that case this input will be connected to the output port. Right? Is it clear? Is it clear what is the switch case? How the switch case is working? How the switch case is working? See here there are the three different input 1 and then input 2 and then this is output. Okay, output, input 1 and then input 2. So this is the control signal, right? So this control signal by default whatever you are going to mention here, so we have scheduled 0 value. If the control signal is 0 or less than 0, then the output is connected to the input 2 is connected to the output. If the control signal is higher than this one, like if it is a 1, in that case the input 1 will be connected to the output port. So this is the very simplest logic of switch case. So we are going to use the switch case to generate a controlled signals. So take this one. So remove the gate pulses. Yes. So just connect the switches. Suppose if you want to get a motoring option, so the input, all the input will be the higher one. Switch 1 and then switch 2, and this is the switch 3 and then switch 4. So here this input we have connected. So this input we have connected. Okay, so this is the PWM input. So now you have an option. Suppose if you want to apply a motoring conditions. So motoring conditions, you can apply 1. Right. So in that case, what it will happen? The input 1 will be connected to the output. If you are applying a 0 value here, then the input 2 will be connected to the output side. Right. So this is the logic which we are going to use in this example. Right. So now take a constant block. So now just to take a constant block, and so now we are going to connect all this port 0, control signal model. So just to connect control signal model. So this is the control signal. So now see, if you apply 1 here, then what will happen? This input will be directly connected to the output. If you apply 0, what it will happen? This second input will be connected to the output. Right. So the second input, how we can configure the second input? So when you can achieve the speed braking mechanism. So whenever you apply, how you can achieve a braking mechanism? See here in this circuit. So we have to remove the PWM here, and then we have to apply a PWM. So switch 2 and switch 4 needs to be connected high, and then at the same time switch 1 and 3 needs to be connected low. So just to take 1. So this by default it will be 1, and take a NOT gate. So by default switch 2 and 4 needs to be high, and switch 1 and then 3 needs to be 0. Right. So this is the control logic to generate a 4 quadrant operations. So now as per our existing conditions, the speed is in the forward directions. So let us take a infinite loop. Infinite, just to take a infinite INF, so that the keep on the simulation will get turned on. The logic is now the entire simulation is in the motoring conditions. If you apply a motor, so we have to take apply 1, and for brake we have to apply 0 here. So this two logic we are going to use it in this block, and this is generalized one. Right, and this is the forward motoring as well as the reverse motoring. If the value is less than greater than 0.5 and then 1, then it's still reverse motoring, and then less than 0.5 it will be a forward motoring. So now we are going to run the motor in the forward direction, and let us check how the braking is working or not. So yeah, so the motor is in the continuously it's running. Yes. So now we have to verify INF, just apply. Just apply here. Yes. Just a second. Yeah. Now first we have to apply infinite. Then only we can analyze it. INF infinite loop. Save it. Yeah. So save. Just to save it. Now you can run the simulation. See here it's running. So now let us check the braking mechanisms. So I'm going to apply see here I'm going to apply a 0. Yes, see here the motor has been stopped. Similarly, you have to release the brake. And immediately the motor will be in the forward directions. And now if you change the PWM from 0.0 to let us take 0.9, sorry, 0.9. So in that case the motor will be in the reverse directions. Yeah, so this is called reverse directions. So 1850 RPM. So like that we can achieve forward motoring and then reverse motoring. Similarly, braking mechanism braking mechanism also. See here again, reverse in motor is under reverse motoring, and see here I'm going to apply a brake. The motor is approached to 0. So like that we can implement forward motoring, forward braking, reverse motoring, reverse braking. So it's a very simplest concept. You please develop your own and then practice this example. Yes. So let's move to the next example. So I'm going to take another example. So this is a closed loop mechanism. So in the previous one we have verified the open loop. So now we are going to measure the motor DC motor speed with the same logic. See here the same logic we have used. The triangular waveform as well as the control signal. So now this controls, earlier we have used the constant block to generate to control the DC motor. So now this signal is a control signal which we are going to drive from the PI logic. See actually here for speed for DC motor speed control. So this is the actual signal omega m. So we are going to take this one, and similarly reference omega m. See here this is the reference omega m and actual omega m. So now we are going to compare these two values. So this is the comparable value. So here the zero order hold nothing but it's a like a similar take a memory block. So it will sample the value and it will keep on hold the value. So like that this two variables has been modeled and compare the value. So see here simple PI logic has been used. Actually I have used the trial and error method. This is the KP value and this is the KI value. So for the KP it's a directly proportional value. So this is a whatever the error signal, it's a multiplied by this value, right? So whatever the error signal, it's the integrated value, and here the integration value is nothing but it's a suppose Ziegler-Nicholas method. So what they are suggesting you, if you want to implement a PI logic, take a one integrator and take one multiplier. So this is the multiplier block, and so the proportionality is from the integrative coefficient as well as that proportional coefficient. So the integrative coefficient must be less than the proportional coefficient, right? As much as less you have to take it. And after this two block you have to just add this one by default in the Matlab. So there are the PI logic also there, PI controller is there. Yeah, so PID controller is there. So this is the very simplest PI logic, and after that this from this speed graph you can get a current reference. See here this is the current limiter. So how much current you are going to allow to take a motor to take a current from the supply, right? So this is the maximum amount of current is 50 ampere. So minimum value is that 0 value. So this is the speed reference graph. And after that, our armature current we are measuring. See here, so this is the armature measurement, armature current measurement. So this same value we are going to keep in this port, in this part, the same logic. So this is the current reference, and this is the actual current reference. And after that, again here the same logic which we are going to use it. So this output will be a 0 to 1 value. So this output will be a 0 to 1 value. So that value is going to apply it in compare with the triangular waveform. So compare with the triangular waveform. So this is very simplest logic which we are going to use it. So now let us run the simulation. So now it is in the motoring mode. See here, we are using 100 radian per second. In this speed unit is the radian per second. So just to open the scope. So here the speed graph. So now the speed graph, and take a current one. So now we are going to change the speed from 100 to 120. Yeah, the speed has been adjusted. Now if you want to vary this one, like if you want to apply a brake, so just apply a brake. Just apply a brake, the speed will reach to 0. And similarly, you have to apply a negative speed like 100 radian per second, and you have to release the brake from 0 to 1. And just change to minus 100. Yes, it will approach us to the negative speed. So earlier it was the positive, and then now it is a negative. So like that you can implement in the closed loop mechanisms. So this is the drive cycle signal. So simply if you connect a drive cycle at this portion, and braking mechanism at this portion, then this DC motor will be perfectly suited for the electric vehicle system. But still in the real time we cannot use the DC motor. So either we have to use, because due to advancement in the motor technology, we have to use the BLDC, PMSM, and SR motor, and even induction motor. So this is the just a proof of the concept, you can use it. So my recommendation you for everyone, so please practice this experiment and replicate the same experiment, and as well as download this project file from this portal, and then practice it. Take output and then share the output in the screenshot. And so the performance of the DC motor is generally for the torque speed curve. For the torque speed curve, generally it will be like this only. It will be like this only. For the DC motor, see here, this is the performance of the motor. So separately excited or say DC shunt motor. So this is a single line. So there is no any range of the performance. So that's why we are calling this is a more perfect motor for the constant speed applications. For the variable speed applications, there is no any there is no any this motor will not suit. So these are all additional applications of the DC motors. So shunt motor is especially meant for developed for the blowers, fans, centrifugal, and then reciprocating pumps, and all other things. Yes, and other applications, just to check it. And the biggest advantages is the high torque, and then simplest control, and then low cost. Whereas it needs a more high maintenance cost as well as the poor efficiency. These are all the advantages and the disadvantages of the motors. Thank you. I will catch you in the next session. Thank you once again. If you are interested in the internship, you will get a certificate by email. For that one, you will get an internship program. So here you can join the VP group, WhatsApp group, and you will get directly, you can get a support from me. how to how to do and how to develop your own vehicle and all. So that is the cost is only 590. The link is available in the description box, so you can get. And if you are interested, is 11th February 2023. 11th February 2023. Right? So you can join over there. If you have any doubt, you can ask me. I will try to give you the answers. And this is my WhatsApp number, so you can post your queries here also. I will give you. I am here to help you. See here, after joining in the internship, you can directly go to the our LMS website. So here you can get a TV bundle. So see here you will get a complete classes. Yeah. So you can download the Matlab simulations. You can download all the presentations, everything. You can download the PPT. You can download the simulation files, everything. You can get it in the internship. Whereas for the YouTube sessions, you can post your queries. You just follow the live sessions, and you can practice on the live only. Yes. So all the sessions are available. If you are interested, you can go and join the internship. You can download it. All the notes are available to download. Thank you, participants. Thanks for valuable time. If you have any questions, you can post me. Just take my number. This is my WhatsApp number. So 9840974408. So if you have any queries about your research activity or your laboratory requirements, you can post your queries here. Thank you, participants. Thanks for valuable time. Thank you once again.